Welcome to this Fireside series. I'm Sylvain Perez, I'm lead product specialist in FluxMotor team. I will present to you the winding modeling for efficient Stator AC Joule Losses computation in flux motors. Then we'll discover how to refine the motor model and how to model losses in the fastest and accurate way. And finally, we'll see how to export to hyperstudy and flux. Let's begin with winding modeling on different examples. The first case is the Prius 2004. We are mainly interested in the winding. There is two types of winding available, the classical and the hairpin winding. We'll focus on the classical winding, and more precisely on the slot filling with coil and insulation settings. In coil settings, we have different sections like wire, slot filling, conductor grouping, and also coil input tables. In the slot filling, we have a random mode, an orthocyclic mode, and a layer mode. This configuration is not valid, that's why we have a gray wire and red icon. In the grouping method, we have horizontal and group method available for this example. In the insulation setting, we have access to the wire insulation. We can add a liner too. At the end, we can adjust the interwire space to fulfill the slot if needed and add twist wire or twist conductor. The second case is the tooth winding. We change the number of slots, the slot shape with an interwire space. Then we can see the slot filling option again and the grouping method with a new method vertical available. Then we adjust the coil inputs with the number of turn per coil, the number of wire in hand, the wire diameter, the interwire space. And at the end, we can adjust really the interwire space to fulfill the slot. The last case is a rectangular wire winding. We change the number of slots, the slot shape again, the slot dimension too. We select a rectangular wire, then we adjust the coil inputs, number of turns, wire in hands, wire dimensions, interwire space. We can add some insulation with conductor insulation, coil insulations. Now we have seen design related to AC losses. Let's see the test with the working point IPN. Here we come back with the Prius 2004 design. We'll see the test working point IPN. We have it in motor convention, in generator convention, but we'll focus on the motor convention in the demo. We have the computation mode, fast there and accurate, but for the fast we have some standard input with the line current or the current density, the control angle, speed. We haven't the capability to address AC losses with the fast model, but we can do some ripple torque analysis. We have some advanced input with the rotor initial position to be in the D-axis with an automatic mode, the mesh order. Then we can choose to switch to the accurate mode, computation mode, with all the same input, but in addition AC losses analysis with different model, one phase, all phase with conductor represented, and an hybrid semi-numerical model. Can adjust the number of computation periods, the number of computation points per electrical period, and we can adjust thermal setting with constant temperature. We'll see other option next. Electronics, power electronic settings, mechanics models. First, let's compare the fast and the accurate model. Fast model gives a really quick estimation with a good accuracy as long as the machine is not highly saturated. Accurate models allows full use of transient finite element models with all the losses computed. We can see torque value are really close. You have DC value with fast, also with accurate, and the possibility to have AC. We have the stator iron losses and air addition rotor. Now let's compare in accurate mode the AC losses model with the two pure finite element model with conductor represented compared to the hybrid semi-numerical model. So we see first for the one phase pure FE model that wall and unwinding Joule losses are really close with three phase represented and very close with the hybrid model. Now let's compare with the twist wire configuration, which have a reversed wire config in each conductors. Here we see the one phase results. We see there is unwinding losses, and with twist no unwinding losses because there is no circulating current. Compared with the hybrid model, we obtain really close results. Now let's compare with the twisted conductor config, which have reverse conductor in slot. We expect to have the same results with no twist, with one phase, no twist, hybrid, no twist, and hybrid twisted, we get the same. Now we'll see the thermal iterative process. Just we have to add an housing, shaft and bearing, define external cooling, internal cooling. Then in the test environment, define correctly the thermal setting with the initial temperature there. And then I recommend to solve a fast mode to initiate the accurate initial temperature with the result. That will save a lot of time in many cases. Then we can run accurate solving with one phase represented with the hybrid model, and if we compare the results, they are really close in terms of thermal, and we can check also in terms of IMAG results, and they are really close too. Now let's discuss about the model computation time and the accuracy. Here we have two finite element models, the one phase model and the hybrid one. And we clearly see both models are really different in terms of node with a ratio of 3. There is a first case with one wire in hand, and we'll simulate it for several speed and a constant wire size. On the base speed point, we see AC losses evaluated with one phase and hybrid model really match with a computation time ratio of 3. We obtain the same result for the max speed. There we have a case with one wire in hand, fixed speed but variable size wire with a constant ampere turns per slot. And we see on the base point that in function of the wire diameter, the model match really good. The computation time is highly reduced. The closer as the ratio 1, the less need to use the hybrid model in this case. Now we have a case with several wire in hand, several speed and constant wire size there. And we see for the base speed configuration, the result match pretty well with a computation time ratio of 5. We obtain relatively the same result for the max speed. The last case have several wire in hand, fixed speed and variable wire size, and constant ampere turns per slot as previously. For the base speed configuration, we see one phase model and hybrid model really match. We see the ratio evolution in function of the wire diameter, and the closer are to the ratio 1, the less we need to use the hybrid model again. The last section of this webinar concerns the export of hyperstudy and flux. So let's see the hyperstudy export first. We select the test parameter in the configuration we want with FE hybrid model to be faster. We select the hyperstudy input, the hyperstudy output, objective and constraints. Then we give a name for the file and we directly create the connector, open in Altair Study. We can run the setup, then to check if the model is okay, and for sure run a DOE or an optimization. Now Flux 2D export with no twist, with represent conductor. We select the model in transient, the inputs, then we give a name and we open it in Flux directly, and we have the model exported in Flux with the conductor. We can do the same for twist wires. And we have there twist wires, as you can see, the switch from the dark to the light color. And we can do the same with the twisted conductor. And we can see conductor has revert in terms of position to the bottom, to the slot, to the top of the slot. And we can twist both wire and conductors. And as we can see, wires are twisted and conductors too. So thank you to attend to this webinar.